So basically, like today, I'll be talking about neural language models, about like the most popular topic nowadays that everybody is discussing. A lot of people are speaking about BERT, a lot of people are speaking about ULMFiT, about GPT-2 and other architectures. A lot of people actually are using them, but unfortunately, the majority of scientists don't really know the details of them because really it takes a lot of time to get acquainted with the details, and also it takes a lot of time like to compare the architectures. So today I will be trying to briefly explain how 3 or 4 main things work. I will try to dive into mathematical details like as far as I can, and I will try to make finalization of what I say by like comparing the real-life performance, by giving some comments about how I used them and what worked, what didn't work, and like something like that. So a few words about OneTouch. What is OneTouch.io? OneTouch.io is the company that specializes in analyzing customized data in the terms of finding GDPR-sensitive information inside their data centers, inside their repos, inside their network elements like sniffing traffic and all of it. So we are trying to make the companies GDPR compliant and like using a lot of NLP for it and using also language models, of course. Okay, so what is the motivation for using neural language models? Kind of obvious question. So the idea here is that continuous space embeddings, they help to alleviate the curse of dimensionality. And the idea here is that actually, sorry. We could use, not that way, sorry. Okay. So actually, we could use discrete space models, and by discrete space models, I mean that we could simply encode different features of words, and actually this way we would also retrieve word embeddings. But this is not the way, because using continuous space embeddings, we can receive the features of different words in terms of their norms, in terms of their distances, and usefully analyze them to receive, for instance, semantic similarity or morphological similarity. We also have the better distributions of sequences of words, and we are able to capture different features and different things that are related to different terms. Okay, so let us begin with it. I will be trying to speak kind of fast because I have a lot of material and I will be trying to tell as much as I can. Okay, so ULMFiT. I think that the majority of people here, they actually heard about ULMFiT, so I will be speaking about what are the details of ULMFiT now. So first of all, before going into ULMFiT, I will say a few words about transfer learning. Everybody heard about transfer learning, but not so many people really know what are the differences between different transfer learning approaches, between inductive transfer learning, transductive transfer learning, and unsupervised transfer learning. So the idea is that we have the source domain and target domain, and we have a source task and a target task. So what is the source task? Source task is simply our feature space and our marginal probability distribution of our tokens, if we're speaking, for instance, about document classification. So what is the task in our case? Task is the objective function. We're trying to learn like the thing that we will be using to predict, to make our inference. And also it is our space of labels that we will be using. So the idea is that for inductive transfer learning, we have these tasks being different, but source and target domains, they may be different or they may be the same. Transductive transfer learning is a kind of different thing. The target tasks are the same, but source and target domains, they are different. And transductive transfer learning, it is less popular, and like there are not really a lot of papers related to transductive transfer learning. And unsupervised transfer learning is like the inductive transfer learning, but different because we don't have the label specified for our data. For instance, for inductive transfer learning, we can have 2 cases when we have a lot of data in our source domain space. In this case, it is similar to multitask learning. And if we don't have it, it is similar to self-taught learning. Okay. So here is AWD-LSTM. This is actually the core of ULMFiT. And like if you read papers, like you always see this AWD-LSTM when people are talking about ULMFiT. So you see here the standard formulation of LSTM. Like everything is very, very standard in terms of like the way LSTM is constructed. But actually, it has a lot of small details that can be used and that make this model that good. And even if you are creating like your own or nano LSTM, the ideas behind the AWD-LSTM, they can actually be used even for your standard neural network, I don't know, for text classification, for instance. So here is the standard formulation for mathematics for standard LSTM and also our stochastic gradient descent. So to recap, stochastic gradient descent is different from other gradient descents because when we're using stochastic gradient descent, we are taking into account each of the observations that we have, and we are doing our gradient steps based on each of our observations. Okay, so this is the non-monotonically rigid ASGD. So ASGD, it is average gradient descent. And the idea here is that we are trying to control our gradient descent by like the parameters that we are having here, by logging interval, by learning rate, and by a lot of other things that we see. And the most important thing that should be observed from this slide, it is validation perplexity. So perplexity itself, it is the measure that measures how well our model performs to predict a new sample. So mathematically, it is 2 to the power of minus cross entropy. Cross entropy is like most frequent thing, most frequent loss function for us to use. So like this is ASGD, and ASGD doesn't return the last iterate as the solution, but returns the weighted sum. Like sometimes I will be using some kind of the citations from the authors here. So this is a non-monotonically rigid ASGD, and the difference here from the standard AGD is that we don't need to control our hyperparameter T. You see big T here. So a common strategy is employed in language modeling is to reduce the learning rates by a fixed proportion when the performance of the model's primary metric worsens or stagnates. So we see here that we're computing validation perplexity. And this actually controls the way our algorithm flows. So this is the idea here, and like just to comment ASGD and AGD a bit more, this is a kind of old gradient descent algorithm, and the worst thing about it is that it was created in 1992, and there are a lot of hyperparameters, as you see here, that should be optimized. It is learning rate, it is initial point, it is login interval, it is non-monotone interval that we need to specify to run this algorithm. So you need to actually do the hyperparameter tuning ideally for this algorithm too, and this is also usually not the best thing to do when you like don't have a lot of time to train your model. So here are other things that are related to AWD-LSTM. This is like you see variable length, propagation sequences, drop connect, and all the other things. I will go one by one to explain what is it in a small words. So basically, what is variable length backpropagation sequences? It is when we are doing our BPTT, like to say it shortly, we're usually specifying one standard backpropagation sequence length, some sequence. And we're using it all the time. But this is not always the best idea because sometimes our backpropagation can't attend to all of the hidden layers that we have in our model. So what is the solution here, and what is the way that it works for AWD-LSTM? We select the base sequence length with to be sequence, and we select with the probability p, and we select sequence divided by 2 with probability 1 minus p. Why do we need these parameters? This is because we are sampling our backpropagation sequence length from a normal distribution, which is parameterized by sequence. So this way we can use our BPTT more efficiently, and we actually have better scores because our model learns to understand different sequences lengths, and this is a kind of useful thing in practice. What is drop connect? So everybody, I think, used dropout. Everybody knows what dropout is. So the idea behind drop connect is that we are not calculating our dropout mask when we already calculated our neurons, like with activation, but rather we are calculating our mask for our weight matrix. And it helps us like to control the flow better. And also, when we're using drop connect, we are sampling this mask again and again during our AWD-LSTM process. Variational dropout. The idea behind variational dropout is quite opposite to drop connect. It is also worth noticing that drop connect is used only for hidden to hidden neurons. And variational dropout, it actually freezes our mask for all the other connections that we have in the network. So it speeds up the computation time. Embedding dropout is also having the dropout for embedding matrices. Unfortunately, it is not really used in production. Everybody thinks that we can use our dropout only for hidden layers and for like the inside of our neural network. But also for our word embeddings, we can also have a dropout. Okay, so wait time. What is wait time? It is simply sharing the weights between our hidden layer and our output layer. So this way we reduce number of our parameters. We can speed up model training. And independent embedding size and hidden size, I don't think they should be commented out separately. And activation regularization and temporal activation regularization. What is it? We are computing L2 norm for our neurons. We're doing it for our output neurons, if I'm not mistaken. And we have R and we have char. Char, it also regularizes our neural network to have the difference between our hidden layers, not for this difference, not to be too big, like for the neural network, not to take very, very big gradient steps, so to control this flow. Okay. Discriminative fine-tuning. The things that I've been talking about earlier, this was about general LM training. This is for the general corpus that we have. And if we're already talking about target task LM fine-tuning, here we're using these things. So this is our SGD learning rule. So looks like the same thing that always used for stochastic gradient descent, but the main difference here is that we are separating our hyperparameters into the layers. So one set of hyperparameters, it corresponds to one layer, another set of hyperparameters, it corresponds to the second layer, and so on. So we have different learning rates for them. So this is simply it. And also slanted triangular rates. This is the way we are controlling our learning rate, to be honest. If the authors are saying that this is the best way for them, then really this is the best way. But from my point of view, I'd rather use some other grad or NADAM to automatically control this learning rate and to use it. But what are they doing here? They are having this set of parameters to control the way the gradient descent goes. So our cut frag is the number that controls for which time our learning rate it increases, and our cut it controls the number of times when our gradient descent it goes down. So you see here so something like that. So our n with index t it is simply the learning rate for iteration number t. Okay, batch normalization. Also, kind of common thing to use. This is also used for target task LM fine-tuning, and we're simply normalizing our layers in our hidden layers inside our network for them not to have their standard deviation, not to have it too big. So we are simply doing the normalization like we're doing it in statistics when we're computing our z value. So it has really a lot of pros in terms of when actually computing batch normalization, we can have our model converged faster than we are not using it. So we can also use less dropout when using batch normalization, and it also increases the stability of neural network. This is kind of a thing too. So a few more words. This is the things that are done for the target classifier fine-tuning. I won't stop on these details on it. And so this is it. This is how ULMFiT works. Explained really briefly, but these are the core concepts behind it. And to summarize, really in a few words, I must say that ULMFiT is always about learning the neural network for a general domain, regularize the network really, really well. And the main benefit of it is that you are using all of these variational dropouts, you're using batch normalization, you are using a lot of stuff that helps the neural network to generalize very well. So this way you can receive actually the model that can be learned on a very, very specific corpus, for instance, on medical corpus. And when you're using your target task classifier fine-tuning, you will receive practically a really good result, even if your domain is very, very specific. But if your domain is kind of standard, sometimes maybe you don't need to use ULMFiT because you don't need that much standardization and generalization of the model. So yeah, this should be like, GIF should be alive, but it isn't alive. Okay, so BERT. What is the idea behind BERT, and what is the main thing why the BERT is so popular? So there was a paper, attention is all you need. The majority of people heard about it. And the main idea behind attention is that we are computing our alignment between our encoder and our decoder. So in our standard flow, encoder reads the input sentence, and decoder predicts the next word that we are trying to predict. So when we are using this new idea, this new attention mechanism, what we are having, we actually have the specific context vector to use for our decoder each time. And each time this context vector, it is calculated in different way. So it is calculated with some kind of this coarse alpha. You see these alphas here. And these alphas are calculated with softmax. I wasn't putting a lot of formulas here because the slide itself, it is not that simple. So we are calculating these alphas, and these alphas itself are calculated by some kind of the alignment model. So this alignment model actually can be anything. It can be feed-forward neural network. So if we're speaking about this slide, here a simple feed-forward neural network is used, and this is the example of additive attention. But any kind of the function that computes similarity somehow, it can be used to compute our alignment weights. And what is the result that we are observing here is that our model learns to pay attention to different hidden states in our encoder, to weight them in a proper way, and to do the next element prediction, next word prediction, for instance, well, like the way it should be doing it. Okay. And here is the slide for our attention mechanism that we can have. This is different types of our attention. I've described additive attention. The main difference is that actually you have the same architecture, but you see the way this function is calculated is different. So this is it. So, and also different types of global attention, soft attention, local attention, hard attention. Different things, it all depends on the number of on how big part of the sequence we are attending. And I will be specifically also be paying attention to self-attention because it is a very powerful mechanism that was developed for reading of the text, actually, for natural language understanding problem. So this is visualization how our self-attention works. So in our self-attention model, memory cell is replaced with a memory network. So it is, shortly saying, it is LSTMN. So it stores contextual representations of each input token with a unique memory slot, and the size of the memory grows with time until an upper bound of the memory span is reached. This is the citation from the authors. So each token is associated with a hidden vector and a memory vector. So we're using a lot of linear algebra inside it, but the main thing is that we're actually computing our attention inside our neural network cell. So this way we can control all of these hidden vectors that we're having and all of the context vectors that we're having, these two main components of our self-attention mechanism. The key idea behind LSTMN is to use attention for including relations between tokens. These relations are soft and differentiable, so when using self-attention, we are using it just like a standard neural net in terms of that we don't need to train the weights on self-attention cells of our hidden elements. We don't need to train them separately. And another thing that was also kind of popular, I've heard about it from a lot of people who are doing natural language processing. This is the neural Turing machines architecture. So neural Turing machines, it is actually the way to look at our memory that we are having. And of course, in our hidden neural nets, on our current neural nets, we are having this memory when we are computing our hidden cells. So Let me show this slide. So we are having this operation that is reading, writing, focusing by content, focusing by location. So what is reading? We are having our big matrix of our memory, and we are weighting each element of it with some weights. We're computing these weights by content addressing, and content addressing is simply performed by softmax, this formula, focusing by content. So we are having our feature vector k, and we have each row of our memory matrix M with index I. We're computing some similarity. Here it is cosine similarity. We're computing our softmax function, and this way we receive our weights. So this is for reading. For writing, we also compute our erased vector. It is vector E with index T. So this is to write something into our memory matrix. We need to erase from it before we write into it. And also, I'd like to show the general architecture. We have this thing. We have three more things here. It is interpolation, shift weighting, sharpen weighting. I won't be focusing on the details of how all of these things are working. It is, from a mathematical point of view, it is a pretty simple thing. Interpolation is computed in a way similar to our GRU cell. Shift weighting, it is simply using the convolution shift. It is actually blurring our information and taking into account the memory from the neighbors of our row inside our memory matrix. And sharpen weighting, it is sharpening out the results that were received from convolutional shift. So the last three things, they are computed for our weight matrices, like for them to perform better instead of simply computing our softmax similarity and all of this stuff. So here goes our BERT architecture. I guess that the majority of people already heard about it, and so I will be saying a few words about encoder and decoder. So encoder, it is computed from a stack of 6 identical layers. Each layer has 2 sublayers, as we see. The first is a multi-head attention. You see it in yellow. And the second is a simple pointwise fully connected feed-forward neural network. You also see it here. And also we computed layered normalization here, and we using our layer norm here. So everything is like pretty simple. It is just all about you having 6 things of it. And our decoder is also composed of a stack of 6 identical layers. Decoder also inserts the third sublayer. You see it multi-head attention at norm, feed-forward at norm. It performs multi-head attention over the output of the encoder. So you see a lot of attention here. And this is why BERT is so powerful. We are computing attention in the encoder. We are computing attention in the decoder. We are always computing the normalization thing. And we also have a feed-forward neural nets that parameterize our approach. The attention that is used, it is scale.product attention. So our input consists of queries, of values, and of keys. Let me show it on another slide. So here, the way it works. So this is, just like I said, it is simply scale.product attention. After the operations that we're performing, we're concatenating everything, and we're doing a linear operation after it. So instead of performing a single attention function with D-model dimensional keys, values, and queries, we are linear projecting them, and we are learning our linear projections. So if you dive deeper into it, it is simply a lot of small components inside our transform architecture. This is how the attention mechanism is working. So you see that this is dot product. It is normalized by the square root of D, and we're computing softmax and multiplying by our weight matrix. And multi-head is all about concatenating these heads. So nothing really very complex behind it. Masked LM architecture. It is a pretty novel thing, at least from what I know, because before it was used and described only in one paper, from what I know. And the idea here is that we are masking some of our outputs. In BERT paper, they are masking 15%. So why do we need it? Why do we use it? Usually, for instance, in ELMo, I will be talking about ELMo later, we are learning our bidirectional architecture. So we have one way and another way, forward and backward ways to calculate our hidden layers. Like this is the concatenation of forward pass and backward pass. So we are doing our masking for 15% of our words because we are trying for the model to try to predict only the things that is masked. So this is not backward, this is not forward, but it is the understanding of the general structure of the language, because language is not always linear, it is not always forward or backward. So this mask, we are replacing simply 15% of our outputs with mask token, of our inputs with mask token. And this way, we can really measure our model very, very efficiently. And also next sentence prediction. So we are combining, just to use our next sentence prediction, we are combining our transformer positional encoding, our sentence embeddings, and our token embeddings, something like that. So this is like the way that BERT performs in our case. So the main takeaways of the BERT that we need to understand, first of all, it is that model size matters. And I must notice that even if you have a really good, very good machine that is NVIDIA V100 and that is very, very powerful, it takes a really lot of time to train very large, like a lot of time. So in the most of cases, personally, I've used BERT-based. So with enough of training data, more training steps, of course, they have the higher training accuracy. But if you really don't have thousands of sentences and documents, sometimes it doesn't really matter. And BERT's bidirectional approach, it converges slower than left-to-right approaches. So this approach that was described, this masked LM, it converges slower. It is obvious, but this is why some BERT predicts new sentences and new words that good. So this is it. This is how it works. Kind of similar to the previous thing, but you see here only two components. This is pre-training for multi-layer bidirectional transformer encoding and fine-tuning. Earlier, we had three components before fine-tuning on the target task. Okay, so GPT. So this is like the smallest part. Let me take good time. Okay, I'm even good with my time. Here we actually have the architecture that is pretty similar to the thing that was discussed earlier, to the BERT architecture. So we also have our unsupervised pre-training for our GPT architecture. So we're given an unsupervised corpus of our tokens. We are also having our transformer blocks. We're also having our softmax. So nothing that different from the way that it was described in terms of BERT. But you see that the way all of these elements of our multi-head attention can be combined, it is pretty different. So our supervised fine-tuning, it is done simply with softmax, and this way we are trying to maximize our conditional probability for each of the tokens that we are predicting. And if I remember correctly, this is it, softmax, transformer block. Transformer block is pretty similar to the one that was used in BERT. And this is our objective to maximize, very, very standard thing. Almost every neural language model has this objective. And this is the way we are calculating our transform part. So also mask multi-self-attention, layer norm, fit forward, layer norm. You see a bit different from BERT, but not dramatically different, I would say. And this is the way we are doing our prediction and our training for different types of tasks, for classification, for entailment, for similarity, for multiple choice. NER, for instance, it is the task of multiple choice, and classification, it can be simple classification of dogs. Okay. ELMo, I guess this is the simplest thing from what I was talking about earlier. And from my point of view, I've used ELMo like the most, comparing to my usages of the previous model. I've been using ELMo more than any kind of other model because it doesn't take that much time for training, and sometimes I don't really have a lot of time for training, and like the deadlines, they are kind of small. So here we're having simply forward LM, backward LM. We're calculating our BLM, like very, very standard thing. And after that, we are combining our BLM representations by weighting them with some theta here. And we can use any other, any theta that we have. We can use the amount of BLM representations that we need. And this way we can fully control our task. From my point of view, I'm using ELMo for my NER architecture. And ELMo performs pretty well. Like from my experience, combined with CRF, ELMo is kind of good. So also nothing very, very different from like a simple standard bidirectional neural language models. Okay, I think this is it. I even have 5 more minutes for the questions.
Now we have a few questions for you.
Okay. Of slanted heuristic or experimental result. To be honest, I can't say that if they done this by experiment or heuristics because they don't describe it in their paper itself. They say that like we are doing it this way. But from what I see and from my experience in terms of learning papers and getting acquainted with papers, this is the experimental result. Because they see that these graphics, it looks like it is kind of good for this specific task. And like it like doesn't converge to something, it's simply like that way and that way. It worked for them, so this is the experimental result from my point of view. As I mentioned, self-attention is all about calculating the attention inside our cells for our neural network. So for our recurrent neural network. So when we're calculating our hidden state and when we're calculating our context vector, we are calculating the attention for them. And this is the main difference. It is like the attention inside the units of the neural net. I would say that from my point of view, this language is kind of similar to the one that we already have, for instance, English-German. I would try using transfer learning, but also it really matters on the corpus. If it would be tweets, for instance, I would retrain it from scratch because the specific properties of the corpus, they won't let me able to train the model well because these are short tokens, these are short phrases, sometimes not coherent corpus. So I would say it all depends on the corpus, but if the languages are quite similar and the corpus is consistent, I would try to do transfer learning. I would say that for training, like you need to have a lot of time. For doing the prediction, it always depends on the hardware that you have. For NVIDIA V100 in production, for instance, this is like the best GPU card that is available on Google Cloud, from what I know. I would say that you can have a simplified version of BERT for prediction if you're doing it on GPU, and also if you're not doing it in real time. I would say for real time, still no, because even these coolest machines, they are not good for doing everything in real time for these complex architectures. So, something like that. Smart prediction is working enough. I would say yes, I'm using it, but I'm using it for data augmentation. I'm not using BERT like to directly do the inference. I'm using it to augment my data and like for pre-processing to do model training after BERT. So for prediction time, I'm using ELMo, and also I'm using hierarchical attention neural nets. It is the like 2-level neural network that pays attention to word level and sentence level representation. So I'm using it. And for now, I'm not really planning to switch into BERT because hierarchical attention neural nets, they're performing quite good. BERT is even more complex, and I'm not sure like our hardware can handle it. Us to remember, like it's hard to say, but to be honest, the first thing is that ULMFiT is all about regularization. ELMo, it is simply bidirectional hidden layers. GPT, it is kind of similar to BERT, but our attention and layer norms are combined in a different way. And BERT is all about attention, feed-forward neural nets, and doing it multiple times. To transform a to actual word representing actual text sentence, word representing text present representations. I don't think I understand how can we transform word representation to a sentence representation, like to predict sentence. If we are trying to predict a sentence, then like it was described that BERT performs quite well like for next sentence prediction, and I think a lot of people seen this demo of like BERT understanding what you are trying to say and given the next sentence that you may be writing, and it works pretty well in that demo that is online. So I think that using BERT is the best idea. And says I need a smaller language approach. Would you recommend? To be honest, I would be trying to use Word2Vec or GloVe, not even go to to these deep neural networks that have a lot of hidden units, and not even try to go into this field. GloVe, BERT, which makes BERT better. Like GloVe is a completely different thing. GloVe is all about calculating conditional probabilities for like two of words and another weighting word, and then this thing is like this division of two conditional probabilities. It is weighted with exponent, and then all of this formula, it goes into, it is like linear regression set, and so you are optimizing actually a linear regression function. It looks like that. So BERT is very, very different because it takes into account the statistical information inside the corpus, and these conditional probabilities are the only thing that is used in GloVe. And BERT is very, very different. It is all about transformers. It is all about multi-head attention. It is all about these feed-forward nets and norms and everything. So I would say that the computational complexity makes BERT better, if I would say better, but it is not always better if you have a restriction on runtime.
That's all. Many thanks, Galina.
Thank you.